Hi guys, welcome back to my YouTube channel. Today we are going to see about magnetic force on a current carrying wire. First, I will explain in brief, then we will enter into our experiment. When a current flows through a copper wire, it experiences magnetic field around that wire. When that wire is placed in between another magnetic field, that wire experiences a force. Here you can see I have placed a copper wire in between poles of a magnet. So when we switch on, the current flows through this copper wire experiences a magnetic field around that, and already field is passing from north to south. So both field will collide or intersect and produce a force on this wire. You can just have a look. To detect the direction of force on the wire, we have to use Fleming's left hand rule. We have to place our left hand in this way. This thumb represents the force or thrust on the wire. This first finger represents the direction of magnetic field, that is from north to south, and the second finger represents the conventional current direction, that is from plus to minus. When these two directions obeys, then the wire will move upward. If any one direction doesn't obey, this wire will go other way around, that is downward. If both doesn't obey, no change in the direction, it will be still upward. The force on this wire can be increased by increasing the current in the circuit, by using a longer wire, and by using a stronger magnet. In these ways, the force on the wire can be increased. Please do remember, the force on the wire will not move along with the magnetic field. Either it goes forward or backward, or upward or downward, not along with the magnetic field. I hope you are getting something. In this experiment, I have used one switch. By using this switch, I can change the current direction in this wire. Let's have a close look at our experiment. Let's start. Here is our simple experimental setup. I have placed bar magnets. This end is north pole, that end is south pole, and a copper wire in between this magnetic field, a cell connected to this wire, and here is a switch which can be used to change the current direction in this wire. Right now, the top end of this copper wire is connected to positive end of the cell, and bottom end of the wire is connected to the negative end of this cell. Right. When a current flows through this copper wire, it itself experiences a magnetic field, and already this wire is placed in between a magnetic field. Always magnetic field will be passes from north to south. Both magnetic field will get collide and a force will be produced on this wire. Let's observe. Ready? 1, 2, 3. Ready? 1, 2, 3. So, because of force, that wire moved forward or out of the paper. Let's observe in this view. Ready? 1, 2, 3. You can see the wire moved forward or out of the page. Let's change the current direction. Now, this end will be minus and this end will be plus. Let's observe what happens to the wire. Ready? 1, 2, 3. Now the wire is moving backward or into the paper. Ready? 1, 2, 3. Let's observe in this view. Ready? 1, 2, 3. The wire moved backward or into the page. The direction of force produced by this wire can be detected using Fleming's left hand rule. Just I have drawn some arrows on my fingers. As you all know, first finger represents the magnetic field, that is from north to south. Second finger represents the conventional current direction, that is from plus to minus. If these two obey, then the wire will move upward. According to our experiment, let's check the magnetic field line, that is north to south. Yes, it is obeying. Conventional current direction is from here, top to bottom. So I am just changing my hand according to the conventional current direction. So magnetic field obeying, conventional current direction is from plus to minus. Then this wire must move outward or forward or out of the paper. Ready? 1, 2, 3. Yes. The wire moved in this way according to the thumb. Let's use again our Fleming's left hand rule. First finger represents the field. Yes, it is obeying. Here the conventional current direction, before it went in this way, but now it is going from down to top. So conventional current direction, I have to place it in this way. Here north to south obeying, conventional current direction is going upward in this wire. Then the force must go backward or inward or into the page. Let's observe. Ready? 1, 2, 3. Here we go. So we can increase the force on this copper wire by increasing current in this wire. By using stronger magnet, we can increase the force. And long wire, if the length of this copper wire is increased, then force on this wire will also get increased. I hope you got it. Let's try some questions from magnetic force on a current carrying conductor. Let's try this first question. The diagram shows a current carrying wire placed between two magnetic poles. The current is in the direction shown. What is the direction of the force on the wire? Option A, towards the bottom of the page. Option B, towards the top of the page. Option C, towards the left hand side of the page. Option D, towards the right hand side of the page. Your time starts now. The correct answer is A. When we look at option C and D, they have given the wire moving left hand side or right hand side of the page. That is not at all possible. Wire will never move towards the direction of the magnetic field. So we have to select from A or B. When we place our left hand according to Fleming's left hand rule, here the second finger represents conventional current direction in this way, in this wire also. So this one is obeying, but when we look at this first finger, that is magnetic field direction north to south, is not obeying in this diagram. So instead of moving towards the top of the page, one direction is not obeying, so the wire will move towards the bottom of the page. Try this second question. The diagram shows a wire placed between two magnetic poles of equal strength. A current passes through the wire in the direction shown. The current causes a downward force on the wire. What is the arrangement of the magnetic poles? Your time starts now. The correct answer is D. Because according to Fleming's left hand rule, when magnetic field direction and conventional current direction obeys, the force direction will be upward. In our question, they have given the direction of force is going downwards, but the conventional current direction is obeying. So, magnetic field direction shouldn't obey for this diagram. So, this end will be south and this end will be north. Try this last question. A metal rod PQ rests on two horizontal metal wires that are attached to a battery. The rod lies between the poles of a magnet. When the switch is closed, the rod moves to the right. What could be changed so that the rod moves to the left? Option A, open the switch. Option B, reverse the battery terminals and exchange the poles of the magnet. Option C, reverse the battery terminals but without exchanging the poles of the magnet. Option D, turn the metal rod around. P and Q exchange. Your time starts now. The correct answer is C. A and D are not possible answers. According to our Fleming's left hand rule, if current direction and magnetic field direction both change means nothing happens, wire will move in the same direction. But here they have asked first the rod moves to the right, then it must move to the left. What changes we could do? So we can change the battery terminals but without exchanging the poles of the magnet. If we exchange the poles of the magnet means the wire will move in the same direction. That is, like before, it will move towards the right, not opposite to that. To make it to move other way around, we have to change either change the magnetic field or conventional current direction. So here in this option we have only reversed the battery terminals but without exchanging the poles of the magnet. I hope you got something from today's lesson. This principle is used in motors. So see you soon with a simple DC motor experiment. Thank you.